So we have an equation here that models the number of algae population in a pond. And P0 is the amount of algae present at time 0. And it is multiplied by an exponential function a to the power of t. So in part A, we're asked to find P0 and t. So to solve for those, obviously, we have two unknowns. We need to set up two algebraic equations. So we are given two knowns. First, we're told that the pond has a population of algae of 2,000 at time 0. Okay, so P of 0 would simply be P0 times a to the power of 0. And anything raised to the power of 0 is simply 1. So P0 is equal to 2,000. And after 15 minutes, we're told that there are 4,000 algae. So that's going to be P0 times a to the power of t. And t should be obviously 15 minutes. And we're told that there are 4,000 algae. So using this equation here, we can solve for a. Divide both sides by 2,000 to get a to the power of 15 is equal to 2. Take the ln of both sides. Or you could take the 15th square root of 2 here as such. And let's see what that gives us on the calculator. Okay, so 15th root of 2, and that gives us 1.047. 1.0473. I'll put 4 decimal places there. Okay. So that answers it. That answers part A. P0 is 2,000. And A is equal to 1.0473. And I'm just going to make a correction here. Instead of us looking for T, we're looking for A. Part B. Find the algae population after 10 minutes. Okay, so, well, our function now is equal to 2,000 times 1.0473 raised to the power of t, and we're looking for P of 10. Okay, so that's a matter of simply plugging in 10 for t as such, and plugging it into a calculator. That gives us an algae population of 3,174.98 algae. In part C, we're asked to find the rate of change of the algae population after 1 hour and after 3 hours. So the rate of change here will be the derivative of the algae population. Okay, so I'm going to differentiate this exponential function. 2,000 times 1.0473 raised to the power of t multiplied by the ln of the base, 1.0473. Okay, so remember everyone, if I have a function that looks like this, its derivative will be b to the x times the ln of the base b. Okay, so that as an aside there. Okay, so now that we have a functional form for the rate of change of the algae population, okay, we can compute the rate at which the algae population is changing after 1 hour, or remember, 60 minutes. Okay. So plug 60 into t into our derivative, okay, and we get 2,000 multiplied by the ln of 1.0473 multiplied by 1.0473 raised to the power of 60, and my calculator tells me that's 1,479.39 algae population growth per minute. Okay, so at that very instant, okay, at 60 minutes, the instantaneous increase or rate of increase of the algae population is 1,479.39 algae. The rate of change after 3 hours, Okay. In a similar fashion, we plug 180 minutes into our derivative. As such, and if you plug that in, we get a huge value of 378,979.37 algae per minute. Okay. So as you can see, after 3 hours, okay, the population of these algae are growing, okay, as our PFT tells us, at an exponential rate.